Well, you were just getting to
Well,
the water hydrogen equilibrium work
yeah,
at Columbia.
well, the problem then was to separate get a separation. And it was thought that inasmuch as there were places around the country that were making a lot of hydrogen, that if you could strip the deuterium out of the hydrogen into water, that you would then get an increased amount. So the idea then was to find out how you could bring hydrogen and water into equilibrium with respect to deuterium, you see. And they set up this, so with Uri set up this operation with some people that were there, using chromium as the catalyst, chromium oxide. And this went along and got to a point where it looked as though it was going to be workable, and you'd want to do a systematic pilot study of it. And so I talked Uri into getting some help from DuPont at that point. So DuPont then sent a fellow up, and they had a group then that worked up the chromium oxide catalyst to where it was successful. And they decided, a decision was made to then make it in large quantity. Meanwhile, Hugh Taylor over in Princeton, and I think this was with the government, with the Columbia contract, worked with platinum as the catalyst. So he moved this along, and that too came to a successful result. So a decision was made at that point to use platinum. And this then was put into a big plant up in British Columbia. Do you know the electric company up there?
I don't remember.
Company, I should remember the name of it. See, I can't remember the name.
Cold
so this was then
River
into an operating plant. And the chromic oxide was made in full quantity but put in reserve. I have this in that
Okay.
Now, the other matter of interest that came along at this point was, and I mentioned this, was where would you go to get a good stock of water with deuterium as your stock material? And so I don't know who did it, maybe I was involved in talking the Army into getting us samples of water around over the country. So we got samples from the West Coast. Now what is that big spring out there in the West Coast, up in the mountains?
I'm not.
Well, there's a name of a spring up there, which is, anyhow, we got water from that spring, and I call it the West Coast Stream. We got water from the Columbia River up there. And then we wanted to find out what was the effect of the rain, the water falling, the condensation as it goes up the mountains, you see. And so the question then was, what is the concentration of deuterium over on the other side So what they got then was some dates over from the desert. And we analyzed the deuterium in the dates. The result was deuterium was high on the west coast streams and low on the dates.
Now, how did you do the analysis for deuterium at that time?
Well, that's another problem. The analysis we were doing, that got started with electromagnetic. And one of the things that I did in the early stages here was to use the change in the index of refraction of water. Now basically, the very basic knowledge that you've got is the density of water. Now George Murphy did those densities. You know George Murphy?
No.
Well, he was there with Urey as a postgraduate instructor or something like that. And so George Murphy worked on getting the densities. And then what I did was to get the index of refraction using very one of those instruments they do for that, index of refraction. And so I was trying to work up a method of the effect of the deuterium on the index of refraction of water. That's one thing I was doing. Now, what we tried to do on the program there at Columbia was to use the density, again, in falling drops. Now, I'm not so sure how this was rigged up, what our liquid was, but I think it was water drops falling through an organic liquid of some kind of just right, and you sized your drops, and then well, that was another method. So, as a matter of fact, later standard of what's the standard company now? New Orleans, the oil company.
Exxon was it Esso then?
No, at the time, you have Standard of Jersey.
Yes.
And what was the one working down well, anyway, George Walden from Columbia went down there as a war job. He was a professor there at Columbia. And he was working on deuterium. They were trying to separate deuterium or doing something down there. So I went down to tell him about what we knew about the method of analysis. Anyway, you asked the question, so you got it. Anyhow, another place that water was picked up was from Norway. And it turned out that Norway water was very heavy relative to all the others. So this got us bothered again. And now, the other thing that happened here was that in Norway they were getting heavy water. I'll just call it heavy water now, I guess. Heavy water by electrolysis. Now, we didn't know what was going on. Anyhow, what happened was that there was a Hungarian, I forget his name now, got a hold of some 100 ml of high concentration Norwegian water. And he brought it to Paris. And now the Germans were chasing through there and were about to take Paris, and he escaped to England with this water. So he had it there in England. And then it ended up by his going to Canada. And in Canada then, he got the neutron absorption of deuterium. And this was the primary information you needed to know, and you had to have a large amount of concentrated stuff to get that. That's how that happened. Now, in the course, I got a small amount of this water at Columbia. And this is what we used to work with. And I would tell the boys that I were working with, I said, now don't you dilute this, because if you do, you're going to get in trouble. Well, they had to dilute it to work with it. And I kept it in the safe. Anyway, you asked about heavy water. Now, the rest of this story is that Urey set up another research job to try to get a bigger factor, and he used amines for this. So we had a very considerable group there working with with trying to separate deuterium in amine systems. I think it was amine hydrogen or amine something like that. Well, it didn't work. It didn't work. And so they tried another one, and this was using sulfite, sort of an acid condition. So you had SO2, you know, H2SO3. And this turned out this worked. But now you see you're involved. If you're going to set this up into a manufacturing operation, you're involved with SO2, you see. So so it was toward the end of things, and nothing happened. Now, and this is a very interesting thing. I wish I could remember the fellow's name, but the project ended, people disappeared, and it turned out that this engineer fella that had been working on this, he couldn't get a job, and while he started putting this together as a process study to see how you'd build a plant with it. And he worked this up, and so he ended up by taking this into the Manhattan district office and showing it to them. And they picked it up, or they put it in their records. And now, what happens? They want a process for making deuterium. And this becomes the process that DuPont used.
This is at Savannah?
Yes. You know about that?
Not much.
Well, I don't either. But that, now look at what happened there. Here this fella did it on his own account. And they pick it up and they use it. Now, I don't know the details of that operation or anything about it, but I just know, I knew this boy very well. We were very good friends. But that's what happens in this stuff. Now I'll give you one other separation, and then we'll go back to the uranium. And this has to do with boron. Now, one time, Teller came through. You've heard of Teller.
Yes.
Teller came through, and he talked Urey into trying to separate boron isotopes, because one of the boron isotopes was very absorptive of neutrons. I don't know which one. Well, Urey, this was part of my job there to look after this, and so a fellow by the name of Kirschenbaum was doing the work, and I blew the glass and set up an operation to distill BF3 to see if distillation would provide a concentration of the boron. Well, we worked a lot. He did all the work, and I'd go around every day, and we'd talk and talk and talk. And finally, finally nothing was coming of it, and Yuri was getting uneasy, and so I said, now maybe we can find a chemical reaction that would be involved in a boron compound, whereby you get an increasing effect of the isotopes. So he did some work in the library and came up with boron trifluoride ether. So we put boron trifluoride in an ether and distilled it, and in the gas, the two molecules are no longer combined. They combine in the liquid. So you have the effect, an increasing effect if there is one. It turned out that it worked. It worked. And so there was built a pilot plant there at Columbia of a tube of about 20 feet high, so that the details will work out how to handle it. Now this was then picked up, and when they got, and they then were sure that they could get that far. This was then picked up by Standard of Indiana, and they made a product then. Now you've got BF3 in really high concentration in the isotope you want. And how are you going to get, and what they wanted was crystalline boron. And how do you get crystalline boron? Well, what was done then was take a tube, like that, about that diameter. You had a tube about that diameter and about that long, and a tungsten wire through it. Heated the tungsten wire, and inside had a mixture of hydrogen and BF3. And now, to our good fortune, the decomposition occurred on the hot wire, and what came out was now crystalline boron. That was a big deal. You got crystalline product there. Well, so now the product was then taken. I wish I knew the company here. It was a company up in New York, chemical company. Could you remember a name like that?
No, I don't.
Huh?
I don't remember.
I see. I wish I could remember the name of this company. But they then proceeded to make the crystalline boron. Now, I didn't take it out to Tiller, and I don't know who did, but I just imagine it got out there. But what he was figuring on at the time was that this would be a trigger for the bomb. That you would have the critical mass put together, and the boron would be on the inside, preventing the explosion, and then you'd kick the boron out, and off it would go. Well, as I understand, it was never used, and as far as I'm concerned, I'm very, very, very happy. This would have been a very, you work toward these things, but then if it happened, fortunately for me, it didn't happen. However, later I found that what it was used for was in an instrument to measure neutrons.
Oh, yes.
Identify neutrons. The BF3 was put in, that's what I understand. So that's boron. Well, now let me get over here to this separation of uranium. You see, at Columbia now, you have Yuri busying himself with trying to separate deuterium. And John Dunning and a couple of fellows over there were, along with Fermi, were doing the physics aspect of this. Now, how are you going to separate? How are you going to separate this? Well, what have you got to work with? practically nothing as far as chemistry is concerned. So they ended up thinking that you had to work with either the difference in weight or essentially the difference in weight. And you could handle that in a number of ways. One would be to put a charge on it, electromagnetic. Put a charge on it, put it through a field, and the heavy one would be held back, and the lighter one would bend over farther. And this was in fact done out at the University of California. And it ended up in a big plant down at Oak Ridge, a big plant, where they built these things, big and tremendous things, and they all had to be high vacuum. And you had a little old channel over here that picked up the light stuff, and another one that picked up the 238. So for the light one then, you had this in there with a bunch of other stuff, and you had to then separate it, but it was now high concentration and you had to watch yourself, because it now had a high concentration. And what they did then was to have Eastman Chemical. You know Eastman Chemical? Is that the full name?
Yes.
Eastman Chemical at Oak Ridge set up a plant to purify this. And you would expect it to be a very simple thing, but it ended up being a very, very complex plant because they had to do it batch-wise. They had to take a batch of some at some concentration and a batch at some other, and this all had to be handled batch-wise, and it ended up with a big and very complex and very difficult plant operation to handle. Well, as a matter of fact, we had gotten along pretty well with our project, and General Groves thought that they needed some help down there. They weren't doing very well. So he had Hugh Taylor and me go down there and look over the whole project and see what we could do, because we were no longer needed, shall we say, up at the other one. So we went down there and looked it over. And we couldn't find anything that we could contribute to it. And incidentally, here's an incident now. Incidentally, Groves happened to be there at the same time, and he had all the Eastman Kodak people come to a dinner. And Taylor and I were at that dinner, and I was over here sitting, and Groves walks over to say hello to me and wonders how we're making out, because he wants us to get over on the project. Now, at that dinner, he gave a speech afterwards, and he says, "Now, I want to tell you, at the end of the war, your children are going to say, 'What were you doing?' And you're going to have to tell them, 'Nothing.'" That's the way Groves work. But that's what happened. Well, all right. Now I want to get back here to what happened. The physics people then, inasmuch as you had the weight difference to work with, you can do it by centrifuging. So here you have UF6, which is a stable gas. You put it in a bowl like that, a big centrifuge, spin that at 13,000 a minute, and the heavy stuff will concentrate out on the outside, and the light stuff on the inside. So what was done, now who did this? Standard of Jersey did this. And what they did then was to have a mechanism whereby they could collect the light stuff out of the center. Now, Standard of Jersey did it, and they brought it to a point where it looked like it was promising. And then in now that's what they did. But that was never picked up then, but it was a couple of years, some years later, it was picked up and made a process. All right. Now, the thing that happened at Columbia then was that they decided that you had to work with the kinetic energy of the molecule, 1/2 mv squared. And so if you take, if you have a gas in a container, a number of gases in there, they all have the same energy at the same temperature. So that if you've got this one, the UF6, 235, another 238, the one will be a little heavier than the other, but they'll both be in the same kinetic energy. Now the kinetic energy is equal to 1/2 mv squared. So here you have 1/2 mv squared of one against 1/2 mv squared of the other. And what's the weight difference? If you have a UF6, the weight is 345 against, I have it in the paper. And then you take the square root of those masses, of that ratio, and you've got 1.004 is all you've got. Now if you take hydrogen and methane, the difference is about 2.5. Now that's all you had to work with. And how in the world are you going to make that work? Well, they talked themselves into looking for some way of making small holes such that one would diffuse through faster than the other. Because the velocity is different. V1 over V2 is equal to the square root of M2 over M1, you see, which is 1.0. So you have a teeny bit to work with. So if you had the hole small enough so that when the light one went through there and it didn't come back, you didn't get too much back diffusion, you could get a separation. That was it. The problem, make a hole. How are you going to make a hole? Well, what they tried to do was to make it from alloys, of which one was aluminum alloys. So you take an aluminum alloy and dissolve out the aluminum, you have a hole left. Well, absolutely nowhere. And they really were working at this for months. And I didn't know much about what was going on, except that I gathered that they were getting into real trouble. They had no way. Now comes the real hot one. Now I have to reconstruct some of this. I heard something about it. But one morning, now over there, the way this thing worked, John Dunning was looking after the physics part, and I was looking after the chemistry part, and Yuri was the project leader. That's the way it worked. So, one morning, a fellow walked in off the street to see John Dunning. His name was Ed Norris. So, I understand you're trying to separate uranium isotopes. Now we were trying to keep this top secret. And here's a guy walks in off the street and say, I understand you're... Now you can imagine what John Dunning did. So I just imagine he was utterly shocked. Now how did you know that we were... How do you know that this, what do you want to do, all that kind of stuff. And then I imagine that something happened, and at the end of the, sort of along here, Ed Norris says, here's a piece of material, a couple of inches square. Maybe you'd like to try it. This is a fact, this is no story. John Dunning tried it. And that piece, I keep telling this story, that piece ended up in millions of tubes, 3/8 by inch by 8 feet long. And that was it. All right, how did this happen? Norris took, but I never talked to Norris about, well, we became very good friends and all that, but I never really talked to him as to about how he got around to doing this. Anyhow, what he did was take a piece of copper with some little holes through it, copper sheet, very thin, put a coating of nickel carbonate over it. And for this, he put the nickel carbonate in water and had a thick slush of it, and he put a coat over that. And then he put some alcohol on that coat, and that fixed it. It made it solid for some reason. It took the water out. See, when you put the alcohol on, then it pulls the water out, and it leaves it as a pretty intact coating. He then plated nickel up through that, through the interstices of that nickel carbonate, and then dissolved out the nickel carbonate, and now you have holes through those needles, and that's what worked. Now, as I say, that was it. But it's one thing to have that, and it's another thing to have a tube 3/8 inch diameter and a foot 8 feet long, and that took a couple of hundred people for another year.
Now, I've heard Clarence Johnson's name associated with this. Did you know him, or did you work with
Clarence
him?
Johnson was with
Kelly's.
Kellogg's.
Yes.
Was he with Kellogg's?
Yes.
And now these people were, all right, now I'll get around to Kellogg's in a bit. But he had nothing to do with this. Kellogg's had nothing to do with developing these things. It was all done at Columbia. But we'll look at the Kellogg's business in a minute. Well, so now you have this thin sheet, which you take it. You can't have that copper there, so you have this. And how are you going to handle that? Now here's the way they ended up doing that. They ended up deciding that, now I wasn't a party to this, that you had to have what was called a base sheet. It had large holes, and this base sheet was about, I'd say 10, maybe 10 mils thickness of nickel powder, a nickel. Now how are you going to make that? So they tried making the base sheet, and here's where Union Carbide came in. Now what Union Carbide did was to take nickel powder, put it in a plastic. What would that plastic be?
At that time,
I can't remember that plastic. A plastic as a thick suspension, and then you doctor that onto a stainless steel sheet. You put that stainless steel sheet into a furnace, and at 400 degrees decompose the plastic, and the uranium, the nickel now is in this tight adhering, but nickel powder. And then you take that on up to, at that time you would put nitrogen in to clear out the products, the gas products, gas nitrogen. And then you take it on up to 1,000 or more degrees, and then these particles will fuse together. And now you, and then you can take that out. Now you have a sheet that has holes that are big, but they're quite suitable to put this nickel carbonate powder on and plate up through that. And that gives you the end product. So, what was done then to make these sheets was to make them make them a foot wide and 8 feet long, and stack them up. This was on nickel, on stainless steel, and stack them in a furnace. They stack here and stack here and stack here, this high. And the furnace was about say I should say about 8 feet square and about 10 feet higher, maybe 10 feet long or 15 feet long. And so now you process them in there through these temperature and pressure, the gas changes. And you end up then, after 24 hours, you get your product. It comes out, it's good. Well, now we had a bunch of people who were working they were on my side of it, separating deuterium, and we had gotten to a certain point on that, and so I suggested, and Norris and Adler were there working away, why don't we set up a group doing basic research on this? So I got Norris and Adler and about 20 other people together, and we set up a research group. Now what do? They work like fools. They just get all kinds of ideas, and here's one of them. You take a stainless steel sheet, you run it through continuously through a furnace, doctoring on the nickel carbonate, and then you have a long furnace and this ended up with Lindy up in New York, where you had a furnace, say something like that, at about 30 or 40 feet long, and you put this thing through, and in 2 hours you got a sheet coming out the other end. It was good. So that was it. Well, now that we tried to make a job out of that, and I'll have to pick up on that later. However, getting back to this, I want to give you another little item here that's very important. When you make this sheet, that's 1 foot by 8 feet, and then you plate the nickel up through that, and then take the nickel carbonate off. Then you have a sheet, a porous sheet, the barrier is called, and then the fine fused nickel powder, but very thin on top, and it worked. Now the question is, how are you going to take that, slit it into little strips, and then turn those over and weld them? This is what John Dunning's people did. Gene Booth and Henry Borst. And they were working, trying to figure out what to do with that. Now Kellex, they had, I don't remember who was on there, but what Kellex was thinking to do, they were going to take these strips and cut them out, and then put them into a rolling machine and do it all in one machine. It was brittle. It would break in pieces. You'd never get anywhere. And I want to tell you, this was, you were at the point of desperation. You had Ed Norris coming in at one point of desperation, and now you have another point of desperation. This stuff is so darn brittle you can't do anything with it. What in the world are you going to do? Well, I wasn't around, but a couple of the boys that were working on this, what they did was take a sheet like that, Now here's a shaft on a shaft on the on a lathe. So here's a sheet that they pasted on one edge of it, and then they put under it a piece of cloth. And then as you roll this slowly and held the cloth tight, you turn this over uniformly without a break. So that got turned over, and then when they had it over, they ran a welding down over, and you had your tube. Now that is another one. Well, you see, Kellex was trying to make this quick like, and this was a hand job. So this ended up, every one of those tubes was made by hand on a lathe over in New Jersey by the New Jersey Engineering Company. And they made them up into the millions. I consider that one of the, here are a couple of the major things that happened. Well, then these tubes were sent out to, I don't know whether the mechanics of all of this, but these were sent out to Chrysler and put into a big reactor of about 5,000 tubes in a reactor. So Chrysler put them together. Now I want to go back to another problem, a major problem. And this problem had to do with the chemistry of UF6, which is a very reactive material. It's very reactive. Now when you get these tubes into such a reactor and you put the UF6 through those tubes, the UF6 will diffuse out through the holes, and then on the outside you collect it and put it into another one. You just build this up. Cascade. So you have then this sequence, and you just have a lot of tubes. And now the important thing about it is that you've made an extremely fine powder of nickel, and the surface area is tremendous, a tremendous surface area. And if you put nickel fluoride in there, it would react with it and hold up all your 235. So that the major problem now was the chemistry of nickel with nickel fluoride.
With the uranium fluoride?
Yes, with the uranium fluoride. Well, this was worked over and talked about and ended up with Bill Libby. You know Bill Libby?
I know. Who is it?
W.F. Libby. Bill Libby was then given the job of looking after this, and Bill Libby was after all, he got a Nobel Prize, you know. Bill Libby was very, very good, and he set up a group of a couple of hundred people with some 10 or 20 PhDs working on this problem. And now, specifically, they figured that you could not have more than 2 layers of nickel fluoride a year added to that. Otherwise, it would hold up your product. Now that means you have to really do a fundamental research job on nickel, which is what Bill Libby did. You have to work with nickel fluoride and copper tubing. So he goes on and on and on with this, and ends up by demonstrating, this was a demonstration, demonstrating that when you had the coating of a couple of layers on there, that then the nickel would not diffuse through that, the nickel fluoride would not diffuse through that and react with the undercurrent nickel. Undercurrent, yeah, the nickel
Lower
under.
level.
Now he demonstrated that. Now that meant that these tubes then, in this reactor, these tubes had to be protected with the coating of nickel fluoride. And so Libby set this all up for Chrysler, and they got all fixed up. They build this thing. And the next thing is, before sending them down to Oak Ridge, they give them a dose of fluorine. They put the fluorine, whew, the thing blew up. Well, it didn't, it melted. Everything melted in there. Now you can imagine, the phone in Libby's office there at Columbia just rang as loud as, and they gave it to Bill as to what happened. And Bill says, well, you mix nitrogen with the fluorine, and that'll cut the rate. They did that. That was it. As far as I'm concerned, that's another one of the major things. So these things. So that's the now.
Now, Paul Emmett, you knew him, or?
Now Paul Emmett came in there and worked with Bill Libby.
Mm-hmm.
Now Bill Libby is a research guy, and he likes to think that way. And he got tired looking around after the overall, or the direction of this group, which is a large group and a lot of people. And so he got Paul Emmett in to essentially look after the shall I say, the overall direction and the administration of this project. But Bill Libby was the working force still. Now that's where Paul Emmett came in. Now, I don't want to say this out loud.
Okay. Let me make sure it's off.
Item that, let me think if I missed something. Oh. I'll tell you this off the record.
Okay.
Let's get to chelates
Okay.
and carbide. Now, you know, first I'd like to tell you about George Felbeck. Do you know him?
No, George.
Do you know of him? Well, it's about time you do.
His last name was?
Felbeck.
Okay.
He ran the plant down at Oak Ridge
Okay.
for Union Carbide. Now, George Felbeck was with the engineering outfit up at in Charleston that looked after the decomposition of hydrocarbons into ethylene.
Oh, he started the direct liquefaction later on?
He built the first polyethylene plant. And of course, here comes Tom Wilson along. But he built the first polyethylene plant. Now, before he did that, and while he was with the engineering group up there, I don't know what, he didn't like much what he was doing or something or other. Anyhow, he went out to California and got a PhD. Now, what's the university out there in Southern California?
UCLA or?
The technical.
California Institute of Technology, Caltech?
Caltech. got his PhD from Caltech. And when he came in, he stopped off to see the executive secretary, this fellow says, I've got a job for you right off, to build it, to design that plant, plant for polyethylene. So he designed the plant, and then they put him over onto looking after the building this other of the Oak Ridge plant, and the future director. Now, here's the point I want to make. Here is George Felber, who was going to run the plant, a top engineer. And what does he do every Saturday afternoon? Comes up to Columbia, comes up to me, and I have a whole desk full of barrier pieces here, and we finger them and look at them and see, well, this will never work, and that won't work. Now, he could have read a report that had come from down here up through a half a dozen places, and you'll finally get nothing but opinions in the final report. George Felbeck wanted his finger.
Real engineer.
And a good many of the carbide people acted that way. Well, that was George Felbeck, and he and I got very well acquainted that way. So, now, as far as Kellogg's, and I don't know anything about this, but what happened in the, I think this happened toward the end of 41 and the beginning of 42, that they got to talking around and ended up that they were going to go ahead with this thing, and right in through the, when did Manhattan District get started?
I think it was in 42 officially.
About what time? The first part of 42. All right. Now they come in, and they then, and who was in this meeting, I don't know, but they decided against centrifuge and for diffusion. That was the decision. Well, and the rest of what went on there, this all got rigged up. I had nothing. Kellogg's comes in now as a company set up by Kellogg as a design subsidiary.
Mm-hmm.
So now, who ran Kellogg's?
Keith.
Thank you for coming in. Keats. He ran this thing. It was down there on 10th Street, New York, and it was they occupied quite a number of floors. That was Kellogg's, and they got this bunch of people. Now the Kellogg's people then. Now you remember who set up did the process study? Later went to MIT.
That I don't remember.
The main engineer.
Sherwood?
No. Was it Sherwood?
I don't remember. I'll look it up.
He was a process engineer. You know what a process engineer is. And he came up, he was the first one to show up there, and I wasn't involved in this because it involved the physics people and these others, so I wasn't at the meeting. But they tried to figure out how to handle this thing, how to set it up into a plant. In other words, a process. And so that's Kellogg's then came in there and doing that. And thereafter then, after this thing was laid out, and various people were involved in one thing or another, the pumps or the separation or all of this, they would come up and run all over the place. Now by this time, you see, here was Uri, and Bill Libby and John Dunning on one side, and I was over here on the other. So the two of us were under Uri. And so I had responsibility for this chemical aspect of the barrier and and for the isotope separations by responsibility. I did, you know, it wasn't like a company responsibility. You were in a little different character. Anyway, you looked, shall I say, I looked after it. And so they were up there running around over the place, and I couldn't stand this. And I told our gang that we've got to write this stuff up regular. So we end up then doing what should have been done by getting regular reports. And incidentally, this is an incident. I said we have to have a summary report here. And so I said, Friday evening at 5 o'clock, everybody starts writing. The whole outfit, and I'm talking about a couple of hundred people, writing a report. And by Monday morning, we had a summary report of our whole separation study. And that became known as the Bible. Well, so I then told these people that they were not to deal irresponsibly with Kellogg's. And then the Kellogg's people came up and wondered what they were going to do. Well, I wasn't trying to keep them away from talking to people. That wasn't the idea. I just wanted our guys to put stuff down in a formal, certain way. So anyway, that's an incident. That's Kellogg's coming in there. Now the Kellogg's people then went along, they designed the plan, and the carbide people okayed everything. You know, they had to okay everything. And meanwhile, carbide took over this whole job of making the barrier. This was started by Engineering of Jersey. They were, and that's where I think Tom Wilson started. And carbide took over that, and they did it over there in where's over in Jersey. Where's the plastic company over there? Bakelite.
It's right across from New York.
Right. Yeah.
Yeah, and all I can think of is
Well, they were over there.
Yeah.
Now that's where they worked up this whole processing of making the barrier, putting it into these big big things, but that was done by Union Carbide. Well, so here you have now the situation that they start up the plant, and that's it. Kellogg's was working there, and that's it. I'll give you another incident. After the plant was running and everything was operating, and after the war, I think this must be, this was in 45. The war wasn't over yet. They decided they wanted an increase in the size of the plant. They're going to, say, get a 50% increase or a 25% increase. And so Kellogg's then got all this, you have to work hard to do a thing like this, design. So they had this all designed and worked, it took some months for them to put it together. So Keith called, I went down, and a couple of us from there went down and got everybody in there of importance, and General Groves. And these two colonels came in and sat up front there with Keith. And here is a pile of books. And so Keith turned them over and said, here, General Groves, is our design for the new plant. General Groves took one of them. What's the Nobel factor? And Keith said, well, there wasn't any Nobel people involved in this. I'll give you another one. Now I didn't know anything about this, and But Groves, these are, I'm just sure about this. Now Groves, you know, when he took over, you know Groves. Now what he tried to do was to get everybody to go to Oak Ridge. And without getting their agreement ahead of time, he went ahead and built a big laboratory setup down there at Oak Ridge and was going to move Columbia and Chicago and 2 or 3 others down there. They built the plant, and as a matter of fact, AT&T's individual who ran the building for AT&T down there, he designed this thing, and he came over and talked to us about it. But they built the plant, and nobody would go down. So there you were. Well, they finally did some other things in it. Now, so another thing with Groves was, as I understand, he would go out to Chicago and ask him about trying to figure out what was going on, and he wanted to make things. So he would talk to him and ask him when they could do it. Well, and I have to imagine, well, we'll know something about this in a couple of months. Well, when would you be able to do it? Well, I don't know, maybe some time after that. He got no answers from them. Now that's the way research people are, and that's the way I am. That's the way research is. If you say I'm going to do something by a certain time, you better leave the country, because you won't get it done. There's nothing wrong with those people. They're all extremely able people. But that's the way it was. He got no answers. Now, as I understand it, when he talked to Los Alamos, who ran Los Alamos?
Oppenheimer?
Huh? Who ran Los Alamos?
Oppenheimer?
Oppenheimer. He talked to Oppenheimer and would say to Oppenheimer, now, when do you think you can get this done? 6 months from now. That was it. And Groves understood that Oppenheimer would do it. And that's why he kept Oppenheimer on, in spite of the fact that Oppenheimer diddled with the communists. Mm-hmm. Now that's a major thing in there, I'm telling you. Well, anyway, that was it.
Now, something about what Hugh Taylor was doing.
Who?
Sir Hugh Taylor, from Princeton. He worked on the platinum catalyst for the...
Hugh Davis.
Hugh Taylor.
Oh, Hugh Taylor.
Yes.
Yes, of course.
Could you describe something about him as a person and his work?
You see, I don't want to talk about people.
Oh, but that's the interesting part of history.
Listen. When I look at this thing, I'm disgusted.
But other people need to know you as a person.
Disgusted. That's why I want to go back home. I'm trying to. That's why I didn't want to talk to you.
No, you were unique in being able to continue science this long.
No, Hugh Taylor, there's nothing I can say about Hugh Taylor but the best. A very able person. And very good at maneuvering things. You know, I don't mean maneuvering at
to get things done.
Management. Now, Yuri was no good at this.
Mm-hmm.
Now, if you'll turn that off, I'll tell you another one.
Okay. You discuss things at Columbia, let's say, with other people, or
we never talked with anybody. Nobody, ever.
Outside or inside?
outside, we, our own people, you know, you work along, and after a while, you don't discuss things with them, other than what you're doing.
You're working with.
Yeah. That's why we never talked about the critical mass.
Now, how did you decide you were going to go to college? Growing up on a farm,
From here,
yes. How did you decide to start
story on this photo, on this work. I started I think his name was James John Livingston Rutgers Morgan. And his people were just that, more Rutgers after all. And now he had been done his thesis in Berlin, or in Germany in the 80s, and was a practical. He was an empiricist along with them. So he wasn't much for theory, but he was doing some photochemistry. And I started on a job in photochemistry. And, as in most research jobs, you start out on this and the ideas aren't any good, and I kept working on it. And I finally got around to doing an entirely different thing. And I ended up with doing my research and ended up with 3 papers were published from it. This is in photochemistry. And then I stay on. Now, then you could stay on at a school. You can't do that now. They hire outsiders. But I stayed on, and they sent me, they gave me this cutting traveling fellowship, you see.
Yeah, did you take German so that you spoke German before you went?
No.
So you learned there?
I went over there, and when I got over there, I was going to try and learn German, but everybody wanted to talk English, so I never learned German. But over there, I worked got around finally working with Bodenstein. Now, if you turn it off, I'll give you another one.
Okay.
And really didn't get anything that was publishable for that year's work there. Came back to Columbia, and by then I was given a course in photochemistry that had been on the books but wasn't given, so I gave this course. And the first year I gave it, Uri was there by that time. He came in and he was writing a book, and I worked with him on he was gotten the prints back, and I would work with him on a copy. So we got together that way. I got together with Uri, and we were thinking the same way, doing the same things. But now, Uri then was interested too in photochemistry, so here I am. I give a course for the first time in photochemistry, and I fortunately had a book on it, Kistikowski from Harvard. And nevertheless, I gave 2 or 3 lectures in the mornings a week. Now, who was in that course but Uri? And who else? There were 2 fellows in there from a physics school, biophysics they call them. And one of them ended up going to Harvard and getting a Nobel Prize for the development of the basic knowledge of vision.
Oh.
And the other one, he ended up during the war by laying out the bombing foundation for for getting a submarine, the pattern, and he got a congressional medal for it. Now those guys were in my course. Imagine me.
You got good questions.
Well, this goes along then, and I'm working on this, and now comes the in 40 and 41. So in the in the fall of 40. In the fall of 40, now they, over in physics, in the beginning of 40, they had been working over there, and I wasn't doing anything about it. But then Yuri came around, and while I was doing my other research, he wanted if I would get the vapor pressure of UF6 over its liquid, you know, the liquid vapor pressure system, and also the triple point when you had solid, liquid, vapor. So that whole summer and fall, I worked on getting the vapor pressure against the liquid of UF6. Now UF6 is very reactive, and you have to work in copper tubing, and you have to work with you can't work with a mercury surface. So I had to have a quartz, a very thin quartz diaphragm between the mercury manometer and between my reacting gases. So I did that, and then in that fall they had gotten money from the Navy Department, now who was working on this down and putting this together down in Washington?
No, but I know the Navy was working on separation, but I don't know who.
No separations. I'm talking about the original managers of this whole project, of this whole overall project.
No, I don't know.
They were related to the Bureau of Standards.
Mm-hmm.
And I'm sorry. Now Yuri was a member of this. Yuri was a member of that. This was the committee, and they arranged all this stuff.
Oh, this was the National Defense Service Committee, or
No, this came later.
This was before that.
Yes,
Okay.
but they arranged all this. And so they got the money, this Navy money, for them up at Columbia for the fall.
Okay.
For 40. And then, between some or other, I had nothing to do with this, but this outfit in Washington, and Yuri was on that, and then they had this other information about 235, uranium-235 and the separation problem. And now this then came together, and they set up a project. What I'm talking about is that the project was set up then, and I don't know quite how it got together. But the project was set up with Yuri in charge and John Denning on the physics and with Fermi there. And then in January 41, I went off Columbia over onto the project full time, and I essentially became Yuri's assistant. So I was Yuri's assistant, and after a while it ended up with John Dunning on the one side and me on the other for our whole project. And I looked after, shall I say I didn't manage, as you don't manage things with Yuri. But we got along extremely well. We understood, we didn't have to understand, we just got along. And I would listen to what he had to say, and he'd give me all these stories, and I'd listen and tell him what I thought, or we just got along fine. And so I don't want to say that I was his, I don't want to set up an organization chart and say that I was the manager of the chemistry, because I wasn't. I just worked back and forth there, looked after, I call it looked after. But I did. I kept things in order for him, and that's what I did. I managed that, managed to look after things and keep things in order for Yuri, and make suggestions here and there, and so on and so on. And so that's the way it went along. And then I got to looking after the chemistry, or the isotope separations, other than and including It is the chemistry of it.
Now, did you get involved with the fluoropolymers or
With who?
the fluoropolymers that they use to make the barriers and?
Oh, I got
Yes.
him immediately in that. And see, I was working with Yuri on this, and anything that's going on, we'd talk about it, and then, as I told you, Norris came in and was working with the Dunning people, and then I don't know. You see, we didn't talk organizational things much then.
Mhm.
But what happened? I'll say what happened was that this job was not a physics job; it was a chemistry job, and so it ended up with me looking after it. And first, what Norris did was to work with the physics people, and they tried to work up something. And then we got over to making more chemistry, and then I look after it, shall I say?
Mhm.
I looked after, and you want to say I'm in charge of them, the uranium research, the barrier research, the fluorocarbon. It's this separation of other isotopes and all of that. So I look after all of that. Well, as for example, I'll give you an example of one. They were involved in the handling of the gas. So you had a pump to do this, and you had to have a valving on the, you had to have valves, and there wasn't anything to use as valves. Rubber would be reactive with the UF6, so you had to look for something else. So we ended up by getting a fellow from Cornell, organic chemist from Cornell, who worked up a process of making a monomer, which would be a double bond molecule with fluorine in place of other things on it as a monomer, and make a polymer of it. And he ended up with making a polymer of that. And so I got around to figuring, how are we going to get this over into the real thing? So I went over and talked to the plastics people over in Bakelite plastic people, they call it the carbide people, and talked over with them as to how we could make a. So they sent me up to Hartford, to the glass company up there, the big glass company that made all the glass blowing machines, and they at the same time were working on plastics. So it ended up that we wrote a contract with them to develop the sheeting of this. We could give them the product, and they would work this up into a plastic sheet from which you would print out rings for your valves. Well, I really looked after all that and managed that. No, that's the kind of thing I did.
Now, where did Yuri fit in?
Yuri?
I don't mean Yuri, I mean Libby.
Oh, Bill Libby ran this. Now here, I'll give you the. I'll give it to you. I'll write it here, and you can put it
Okay.
down if you want.
Yeah.
Harold Yuri, leader,
Yes,
and then you branch out. You've got John Dunning.
yes.
Under John Dunning is Gene Booth and Henry Bourse.
Gene,
And then over
I'm not as fast as you are. Henry Bourse,
Gene Booth,
yes.
Henry Bourse.
B,
They looked after the physics.
okay.
and over on the other side was me.
Okay.
And I look after the chemistry. I look after the the barrier, let's call it, the barrier research and development.
Okay.
I look after that, and I look after the
Separation.
deuterium work and the boron, and that's the isotope separations. Well, that's about, so if you wanna, now Bill Libby, I forgot. Now Bill Libby is I don't like to say he's under me, but he was.
Okay. Facts are facts.
Now that was a major, so that we had 4 major groups.
Mm-hmm.
One was with Gene Booth on the actual physics of it.
Okay.
The other was with Henry Bourse on the pumps.
On the pumps.
Yes, and Bill Libby on the chemistry of nickel and UF6. And then,
Engineering.
I'll just think of somebody. You see, we didn't have a real. I guess I looked after most of the other research end of it over there.
Mm-hmm.
But now Bill Libby was a major. His was a major project. Now those were the major project. And but that's Bill Libby was it. You know, after all, look, that's one of the major things to be done. And he did it.
Yes.
Now you know what he did later? He then went to Chicago.
Mm-hmm.
I'm thinking, yes, Chicago. Yes, of course he was in Chicago. Now, I'm just trying to think, was he on the project? And you see what they did at the end of in 45, they were trying to rig up what they would do, what some of these people would do, and they ended up with setting up a nuclear institute in Chicago with Fermi and Urey.
Mm-hmm.
And in 45, I was invited out there to join that institute. And I was offered the job. And at that time, I could stay at Columbia or go to Chicago on that, or then they were starting this big project on coal hydrogenation down in Charleston. So I ended up going to Charleston.
Yeah, how did Union Carbide come to be interested in coal liquefaction?
Back in the 20s, George Kerm had a fellowship out in Pittsburgh. This fellowship was to make chemicals out of acetylene. So he and George Davidson later got to working on it, but he tried to make chemicals out of acetylene. Now the reason for that was that carbide was started on calcium carbide.
Mm-hmm.
You know about that?
Yeah.
Out in Chicago.
But I don't know the details. No.
Well, I don't know, but that's as a story. In other words, calcium carbide was a major product, and acetylene is made from that. And so here they were trying to utilize acetylene to make more chemicals. And every darn thing that he tried to make out of acetylene, he could make cheaper with ethylene. Now, I'm not sure whether he made it there or later down at Charleston, but they got around to making ethylene glycol, which ends up as the anti-freezing agent. You know what they call Prestone. Now, Prestone became the product, and that's what made the chemicals company. That Prestone. There it is. That made it. That Prestone. Well, you see, in making the Prestone, they then had to make ethylene, and they had ethylene, and they could convert that over to ethylene oxide and the Prestone, and then they work up this whole systematic aliphatics chemistry. So carbide made aliphatics chemistry. That was it. And it all stemmed from that. That was carbide. Now, you see, that was based then on ethylene that they got from, and they decided to, I don't know what went on, but anyway, a plant was built down at Charleston using natural gas. The heavy molecules of, that is ethane, propane, butane, in natural gas were then put through a high temperature furnace to crack to ethylene. And that was it. Now, the big thing that they did that made this whole business was the purification of ethylene by low temperature fractionation. That was really the big thing. Low temperature fractionation to purify ethylene. And then with pure ethylene, you see, you could go to all these other things. And look, what happens then with the, well, you know about polyethylene?
Very little. I've heard George Young talk about it once or twice.
Who?
George Young.
Young?
Yes, from Union Carbide.
Well, he'd know more than I do, except that the one thing I know about it is that, just hazy, is that who was this fellow up at Lindy? He was working with various things and was doing some high pressure studies, and he tried high pressure on ethylene. And he got the pressure up to some 20,000 pounds, and he got the product. Well, that's how that came into carbide, but it had been developed also over in England, I think, and so come the war period, the polyethylene got to be important because of its electrical properties. So they wanted a plant to build it. And this is where then Felbeck came in to design this plant. But they had done work, by then they had done more work up at Lindy on it, you see. Trying to work it out.
Why would the person have been interested in pressurizing ethylene? Studying ethylene under high pressure. Do you remember why he was interested?
The same reason that this other guy up there worked with trying to make zeolite out of synthetically.
Okay.
That's the way things happen. Why did Ed Norris try to make that? Now I can tell you another one. I showed you this log plot, didn't I?
Yes.
Why did I think of that? It was absolutely unreasonable. I didn't reason to that. I call them happenings. Now I'll tell you another one. You've heard of Priestley?
Yes.
Well, in them days they were working with mercuric oxide. And they had then ways of handling gases by collecting them over water. And so here was, you read back over what he was doing, and so Priestley, among other things, he was heating his mercuric oxide and getting the oxygen, and then he was collecting it over water. By then they were doing that. And here he had this, and he writes this. He said, I had a candle there and I thought I'd stick it in. He stuck it in, poof! What did he discover? Combustion. Why did he do it? I had it there and I just stuck it in. Now, in the cellar, as I understand, he had some plants growing underwater, and there were gases. You know how they do it? You have gas on it. He collected this gas, and he tried to candle it. What did he discover? Photochemistry. Look at that. And then he discovered that oxygen in the first place, and what happened with that? He was arguing around about this, and then Lavoisier over in Paris picks this up, and now you see you've got oxygen, and oxygen reacts with all the metals, and the metals, these oxides interact with each other, and you've got then you've got the whole of inorganic chemistry. And now, instantly, overnight, Lavoisier puts this together. And that's chemistry. Put together just like that. Now that's the way I think, that's a happening. I think of them as happenings.
That's a good description.
Yeah. Now, you know, some years ago they talked about happenings.
Yes.
They don't do that anymore. But the more I think about it, the more, and it's something that goes on in your head, and which you do without thinking. It's like if you're thinking too hard, you finally give up and go to bed. And the next morning, there's the answer. And the way I see it is that your mind is an interlocking electrical establishment, and you've got all these things going on, and then it will, on its own, it'll go and pick up things. How do you remember something? See, I couldn't remember Keith. How do I remember other things? We had a new president here. He came from Canada. I couldn't remember his name. So I thought finally, a new president, so what? You know his name? Sawatsky. S-A-W-A-K-S-S-S-K-Y. So for a month or two, I remembered a new president, so what? Now that's what your head does. Sawatsky. That's what I didn't tell him.
Well, how was Union Carbide planning on getting ethylene from coal liquefaction, or was it just a source of chemicals in general?
No, what the problem was that there. See, I really didn't follow this up, but the problem was that they were losing this resource material. And so it got over to where ethylene, by this cracking of the natural gas, got to be there, and the whole outfit was built up down there. And by through the 20s, through the 20s and the 30s, they got up into a plant which at that time was must have been up toward a visit. But it was on they had the mining there and they had the gas, so they had cheap energy, and you had the Kanawha River, which is water. You have to have water for everything. So that's what put the plant there. As a matter of fact, there's a gas plant there. You talked to Tom Wilson about this. There's a glass plant. Monsanto had a plant. DuPont had a plant. And they had a lot of other plants. And you know down there that they had at least 6 major professional outfits held monthly meetings in Charleston. You go to Harrisburg, there isn't one.
Mm-hmm.
I'm talking professional meetings. I'm talking engineering society, mining society, and all that, and chemicals and physics. In Charleston, West Virginia. That's Charleston, West Virginia. And that's what made it. So now they're running out of gas. And what are they going to do? They have coal. And you've had this work on Fischer-Tropsch,
Mm-hmm.
and you've had the work on hydrogenation. And meanwhile, over some years there, in the later 30s, they had been doing some research on hydrogenation of coal, trying to get over to something. And so after the war then, they up and decided to, because things were beginning to get tight then, and they decided to have a major project on trying to get ethylene from coal. That was the idea. Now here's the problem. Ethylene is from ethane, which has 2 hydrogen. You knock those off and you have ethylene.
Mm-hmm.
Now, if you look at coal, coal is a ring, benzene, and you got the benzene and naphthalene and phenolphthalein and these other high and so on. So your problem then, and in the coal hydrogenation, the problem was to hydrogenate those. So the essence of the success would be the cost of hydrogen. That was it. That was the major problem. How are you going to get hydrogen cheap enough? Well, so they started the project anyway. They started the project, and so what did they do? They have John, they have Oswald, George Felbeck in New York is running this thing. And now one of the reasons they could embark on this was because back then the government allowed you to take your research and development expenses onto manufacturing. So you could, before making your tax, you see, you could account for your cost in considerable part that way. It was quite a considerable part. So partly because of that and the absolute need for it, they set about this project of making from coal. However, the problem, you've got essentially coal is CH, and you've got to make CH2. So you've got to put that in. So you have to have the mechanism for doing it and the price, and you've got to get the hydrogen cheap because it's under pressure, and so that costs a lot of money to get the pressure. So that then set you up to do the design of the plant, and they had all the German stuff that they could find and to work with, design the plant, and the work that they had done here. So Paul Oswald and of course Uri, of course Felbeck in New York was running this, but Oswald in Charleston designed the plant. Now the plant was to be a 300-ton-a-day plant. Now you talk, Tom, you know You want to know about this? Don't talk to me, talk to John Potter.
John Park?
You know, Potter's the guy that wrote this all up and did absolutely tremendous job. Have you seen it?
I saw a report that Tom Wilson gave me, just one report.
How big?
Oh, it's probably 100, 150 pages.
Well, then you've got the final report.
Mm-hmm.
Well, that's it then. So don't talk to me. Except that I will say that, and I just stress these aspects of it, and the hydrogen was the aspect. How are you going to get hydrogen? Well, them days they were talking about, by then they had gotten information on these underground gasifications that had been done in Russia. So they thought about, here you've got these hills and the coal vein appears on either side, so why not dig a hole and do an underground gasification? Now, in underground gasification, what you have is, first, you want to write a simple reaction. CH plus oxygen to give CO, and if you got enough oxygen, go to CO2. Otherwise, it'll be CO. And if you have water along with that, and if the temperature is high enough, the CO2 reacts with the water, gives you CO. So here was the idea, that you'd have a pipe, a hole, and you'd feed air or oxygen. As a matter of fact, you end up feeding oxygen in with steam. Oxygen and steam, and you get out on the other side carbon monoxide. And then you convert the carbon monoxide over to hydrogen. CO plus H2O will give you H2 plus CO2. And this is a normal thing that's done. Now that was the deal. That was what was figured out. So they were trying to figure out how to dig a hole in there. And a couple of us were up looking at the airport one Sunday and saw a boring machine they had, dug a hole to put in an explosive. And they dug a hole about a couple-inch hole. So we went back and told Ospa about it, and Yuri, and Felbeck. And they up and then got one of these machines and started drilling. And this ends up with a hole, a machine drilling that was on its own tractor with cutters going in 4 feet high and 6-8 feet wide, going into the hole, and the hole being trailed out over you know, what do you call them? Carriers out. So the machine conveyors. Separate conveyors. One would dump it on the other. So you hang, as the machine went in, you hang a new conveyor on, and it conveys it out. So it would go in and cut a hole that size. And that brought coal out at 25 cents a ton. Well, in 50, somewhere around 50, they had a lot of acetylene down in Texas that they couldn't use, and they wanted to see if there was a way of using acetylene. So a fellow by the name of Roberts and I were sent over to Europe in 50 to see if we could find the acetylene process. And nobody knew anybody then. We had no letters of introduction or anything. We found out who was where by looking at the Chamber of Commerce reports. Anyway, we wandered around. Now, and I decided that I was going to go and look at this Fischer-Tropsch research plant over there. Where is that? Where was that?
Was it Mulheim or?
the town, in Essen.
Yep, okay.
Yeah, it wasn't Essen though. That's one of those names I can't remember.
They had the research center at Mulheim, but I don't know which plant it would be.
No, but it was, I just can't pick up this name. But this was the researcher's thing. Now, what I had done by that time, I thought when we were going over there, why don't we take they'd made a
Film?
film of this machine, talking film. And, film of this machine. No, there was no talk on it. No, just a film of the machine. So I thought, why don't I take this thing along and see if we can do business with it over there, see if we can find somebody who might be interested. So, and the other thing, so I thought, well, I'll go around to this Fischer-Tropsch plant, and I was in that area, and I went around. So I went around, and I was talking to the fellow who was running it, and he, among other things, we were talking about, and so he says, well, I'm very much interested in this. We're very much interested, but we couldn't use it. We'd have no use for it. And he said, you want to show this to the people over in Essen? So I said, okay, I'll be back. I'll be going down to Munich, and I'll come back here on Saturday. So I came back Saturday. And meanwhile, he said, we'll show this, if you don't mind, we'll show it to my people. So after lunch, he brought his whole gang in, about 50 people. And I showed it to them. Of course, they were all intensely interested. And then Saturday morning, I went over to his place, and it was then foggy to the density that you couldn't see your finger. And Essen was about, 3/4 of a mile or an hour from there. That's what I'm trying to remember the place. So we couldn't go. And after about an hour and a half or 2 hours, we managed to get over there. And when I went into this room, here was a room full of about 35 people. And these were the big shots of the mining industry. Had been waiting there. The big shots. So I have to stand up and give them a talk as to why we did this, and I did. So I stand up and give them a talk about it, and we go through it, and I tell them why we did it, and so then we show the picture. And in this picture, what they had done in order to show how much coal was coming out, they had two guys there on the outside trying to shovel it away, and it just covered them. And when this part was showed, the guy hammered his, one of the guys hammered, he said, that's the first time I've seen Americans work. That was funny. Now they were intensely interested, but they couldn't use this in Essen because in Essen, the coal is in rolling seams, 1,000 feet down. And they have to put ground back in, so they couldn't use it. So that was that. Well, let me see, there was another about our coal hydrogenation project. We went along, and these guys did some really good things. You talked to John Potter about this. And now, why didn't we get a plant? Every time we got around to where we thought we had a working plant, we discovered more oil. That's a fact. So every time we thought we had something, the price of oil would go down, and we never made it. simply never made it. Now, one place where we thought we might do it was in Australia. Because there, what's the big place in Australia? They have a big mountain area that rises 50 miles back, and so you have coal available, cheap, like in South Africa.
Mhm.
So they wanted to then utilize, there was a chance of utilizing, so we talked with the people then from Australia. And as a matter of fact, as I understand now, when Telbeck, on his final vacation, he ended up, he and his wife were going to go to Australia, and he was going to explore this further. And we had talked with him time and again. But he was, and you know what happened to him. Oh, you don't?
No.
They took a plane in New York. The plane went up, and the birds clogged it, and it dropped right back into the bay. That was it. That was George Phillips. Now they don't, birds don't do that anymore. But that's what happened to George Phillips. So we thought we might do it with Australia. It never got around to a process. Now you want to know about coal hydrogen? You got the guy that knows all about it, and that's John Potter. He's a very able guy, and he knows all about it, and so on. So that's, but it was the, we never made it. Now, meanwhile, along with the hydrogenation, we were doing the research, and one of the research jobs was on Fisher Trout. And Tom Wilson was doing that. So Tom was doing research. Now when you get over this polyethylene business, you know what Tom did, you know more about it than I do. You know?
No.
Oh, he, no use for me to tell you.
No, I'll just him.
You go after Tom,
Okay.
I'll just give you a hint.
Okay.
That's all it is. But we had come to where there was no much point in doing research anymore on our job. So we got around to where they wanted us to look at it. Another major problem was this ethylene. And so in talking around, we thought, well, maybe Tom Wilson would be a good guy to start working with ethylene. So Tom Wilson and a bunch of guys then got together and started on ethylene, polyethylene. And now, when they first started polyethylene, that first plant ran at around 20,000 pounds. And in the first plant, all too often it would explode, blow up. They put in another reactor, you know, a little small reactor, because when you condense it, when you polymerize it, heat's skipping out. So you've got to pull out all that heat. And that would cause it to blow. And so that would go on. It blowed up now. And so in the course of time, they finally found out why that polymerized in the first place. Because there was something in the atmosphere that got into that ethylene that catalyzed it. I think it was an oxide of some kind. You know, an impurity in the atmosphere. Mm-hmm. Now, either Tom or John would know more about this. In other words, they got around then to seeing it was catalyzable. And so by then, Tom started working on the catalyst activity of polymerization. Now, I went up to Tarrytown and then left there after 3 years and came down here, and Tom Wilson kept at it. And Tom Wilson got the pressure down to 400 pounds. You know what that would do. And furthermore, now he can tell you more about this catalyst. Now, that's what I wanted to talk to him about when he got up here. All I knew was that when the leverage job came along, you know what I'm talking about?
Nope.
Well, of course you do. They tried to take over Union Carbide.
Oh, okay, yeah.
When that leverage job came along, and the stock went down, and everything else was happening, I was absolutely convinced that the only reason carbide stayed on its feet was Tom Wilson and polyethylene.
Okay.
Look what polyethylene is now. You can't get a paper bag anymore.
No.
That's Tom Wilson. But you see, I haven't been able to get it out of him. I haven't seen him. I didn't see him till the other evening up here. I haven't seen the guy. But as far as, I'm just convinced that that's Tom Wilson.
I'll have to have him over to
And that Tom
Lexington.
Tom did that. And so I'm just hoping to, anyway, that's all. That's about it now.
Now, how did you end up going to Tarrytown? Or
One day they I went up to New York to talk to Felbeck. You know, as I did about every 3 weeks. And he said, now this was toward the end, this was in 60, what is it, 90, 59, 58. This had been 58. He said people have been talking to me and they'd like you to be the director up at that institute they're building up in Tarrytown. So I said, director? You know, you talk around and you know about the institute?
I don't know how it came into being, no.
Well, just very briefly, I don't know too much either, except that in a couple of years there, they were toying with this government contract of making of studying the reason for the basic understanding of brittleness in metals and substances. That was what was, and now who's the outfit down in Washington that has this kind of, it is a Navy, Colorado is a Navy, it's basic research, ARPA. You know ARPA?
No.
Okay. Yeah, I think so. They put out these projects for jobs that were not well defined, and this was one of them. And so they were prospecting to set this up, and there were people working on it, and they ended up writing up a contract for it, which was accepted. And then they decided that they would build this research and to shall I say, utilize this as a means of building a basic research institute for the corporation itself, but utilize this as a starting help. And that's the way it went along. Now they got as the director, the let's see, I can't get his name. The fellow who was the director of the chemistry division out at Los Alamos. Eric. Well, he got his research, he did his research at Columbia, and then went over to Denmark and did some work over there. Anyway, he was working around, anyway, he ended up as being the director of the chemistry, the whole chemistry outfit out at Los Alamos. Well, they persuaded him to be the director of this institute. And they also got as his assistant, Shoemaker, who had worked for years with out at Caltech with who's our Nobel Prize Peace Fellow?
Pauling.
Huh?
Pauling? Linus Pauling?
Yes, Pauling. So he worked with Linus out there for some 20 years. So Shoemaker, so it was Eric, maybe I'll think of his name, and Shoemaker. And they had a group of about, I don't know, 20, 30, or about maybe 50 people altogether. But the building wasn't up, and they were working over there in New Jersey, over in that great big park over in New Jersey. Lindy had a place over there. I can't remember that either. And so, as I get it, the management in New York said they wouldn't build it as long as this other fellow was the leader. Not because he wasn't any good, but because he didn't know carbide. And he thought in terms of basic research for basic research. And so they ended up saying that they had to, if they were going to do it, so here I was from Columbia and from this other thing, you know, Manhattan District Business, was down there and worked with, and once a month we'd go to one of the other places and listen to what everybody was, you know, about a half a dozen of us. Me from our group, somebody from Lindy, and somebody from National Carbon, and somebody from Electromet, say a half a dozen of us. You know, people were involved in looking after research and development. We get together about once a month, go from one place to another. And so I knew all these people, and I think I knew more about what else was going on, because what are we going to do with our plant? We were going to make graphite for Electromet. We were going to make national carbon for National Carbon to make electrodes. We were going to make carbonic acid, the other acids, for the plastic people to make polymers, because that's what got plastic started. Bakelite. Bakelite is phenol acid, it's phenolic acid. And then the gases would go to the chemicals company. So that was the setup. And it was, you know, look at it, it looked as though it was something worthwhile. That's why they did hydrogenation. It looked great. So, by reason of that, I got to know a lot of things that other people didn't know because you got around that way. So they says, Felbeck said, they want you. I said, so, what do you say? He said, well, and so on, you know, we talked back and forth. So I ended up going up there. And I told you that when I went up there, I didn't like what I saw in respect to the distribution of the budget. And so I was kind of shook about this, and I really set my head to see if I couldn't work this over. And one of my workovers was nothing other than a fellow by the name of Radeau. That was it. Well, now, the other thing that I experienced, and I think you mentioned this on the way down, we worked at this. Now you can see who these people are, and they're good. They're all very good, and they work well. What, for example, what they made was, I think, was cadmium, a carbide. I don't remember the name of it. I don't think it was a cadmium carbide. It wasn't silicon carbide. But, for example, one of the things they wanted to do was to get the tensile strength of it at high temperature. So here you have a furnace with a little tube of this, and you got to make this thing pure to begin with, and then you got to pull on it to see what it. So that is a major job. And that's one of the things they would do, looking at the basic aspects of this. That's the kind of thing. And every 6 weeks we'd go, every 6 months we'd go down to, about every 6 months we'd go down to Washington and tell them what we were doing. There was nobody there that was interested. They had us what do you call them? It's not a supervisor.
Technical.
Another outfit that looked. Huh?
Yes. Like Burns and Rowe is a consultant.
Well, it wasn't a consultant, but it was something else. Anyhow, our consultant was this outfit down in this Army outfit down in Atlanta. Do you know the name of it? That big Army plant down there.
No, I don't.
What was going on there was all of that research that ended up as NASA.
Mm-hmm.
That all was going on there. They were looking for a solid fuel at the time.
Mm-hmm.
So we talked to and that was a good place because that's after all what we were interested in. And they were all interested in what we were doing, and we were interested. And they showed us all over and showed us everything we were doing. But here's my point I want to make. I couldn't find anybody that said, now look here you, let's get at this thing and do something about it. I couldn't find anybody.
They needed the general growth.
They were interested, they couldn't have been more concerned, but they didn't get in there and say, now let's do something about it. I ended up thinking, if anybody's going to do something about this, it'll have to be me. This project.
Mm-hmm.
Well, so I says to myself, I said, now look here, let's just see if we can't figure out that by this time next year we're going to make something that they can test. I'll see if I can do that. But that's, now let me give you another example of this, the way this kind of a thing works. When we were working down there in this coal hydrogenation business, now George Felbeck was interested in doing things quick. So he wanted to do this hydrogenation fast. So he figures we'll do it not at 500 or at 350 or about 400 degrees. We'll take it up to 800. We'll not do it at 3,000, we'll do it at 15,000. For that, we ended up with a little pilot. And you know who was running this pilot plant? Tom Day. And George O'Connor and Jack Potter. Potter knows about it, but he wasn't directly involved, but it was Tom Day. And Tom was just it. He was wonderful for this. Here you had a tube that was, say, 500 feet long. It was 3/8 inch diameter, and the walls were about an inch thick. 3/4 of an inch thick, stainless steel. That was it. So one time we were talking to George Davidson was down there, and we were telling George Philbuck and Davidson we were talking about it and saying what we were doing, and Davidson said, "Well, when do you think you're going to get to it? Get a result here, get it working?" And George says, "Well," this was in June, I guess, "well, I think we'll do it in October." I'll be down. You know what that did to us?
Got you going.
George Davidson said, "I'll be down." So every morning we got up, George Davidson will be here in October. That's what does things. That was General Groves. But that's what does things. Otherwise you diddle, as you have to. You see, when you do things like that, you got to know what you're doing. But before that, you have to do this diddling. And that takes time. You don't know how much it is. So,
Now, was the person that was working on that led to Zeolites Beck at Terrytown?
Beck.
Mm-hmm.
You were right. That was Beck. He didn't do the ethylene, however, but it was another fellow. But that was Beck. You're right. Now, I don't know how he and Rebel got along, but they must have got along pretty well. But I don't know how it got around to where Rebel ended up doing it.
Mm-hmm.
You know, it's just one of those things.
Yep.
But here, what was his name?
Beck?
Beck.
Mm-hmm.
Now, why did he do it? But he didn't tell anybody. Because if he'd told the director would say, "Cut it out and go and do something else." Well, there are all kinds of things we can talk about.
Now, you were mentioning Rabeau. Would you like to go in a little detail about Julia
About what?
Rabeau? Julie Rabeau?
Oh, I don't really know much about him, personally.
Mm-hmm.
Except that he came over here and we got along very fine. But personally, I didn't know him real personal like. Now he and Shoemaker were the ones that were just like that on the project.
Mm-hmm.
Just wonderful for Shoemaker. Oh, incidentally, let me tell you about that outfit up there. They were doing. This was supposed to be a basic research outfit, and I wanted to keep. I had two problems there. One, to keep them minded for basic research, and then another to get them out and become acquainted with the Union Carbide's affairs and be worthwhile, do practical things. Now, in basic research, it turned out Louis Hammett left from Columbia. He was at Columbia. So I thought, why don't I get Hammett up here for a semester? So I talked to him, and we arranged to have Louis Hammett come up there for a semester. He said, what am I going to do? I said, you're going to just hang around and go around. So what does he do? He goes around and talks to people. And he had other contract, and I said, well, don't worry about it. You can do that better than I can tell you. And so he went around, he talked to everybody, and really being there was a major stimulus for people to think. But that was Louis Hammett. He spent a semester. You know Louis Hammett?
I know who he is. I don't.
Well, yeah. Well, that was Louis Hammett. He was very good. So I was. Now the other problem was how to get people. And what I tried to tell them was this: that they were to get acquainted with whenever they had opportunity, get acquainted with somebody down at Charleston, or in the carbide business. Become familiar with what they're doing. And then to get them interested in having you do something up here. And then I said, now when you do something, you give them credit for it. That's right. And if I could have made that work, we'd have had a place up there. Because that's the way things work. You look around at all these things that work, and that's the way they work. And if I could have gotten people to work up there, get acquainted with others, help them out, and when something came of it, give them the credit for it. That's when you get it going.
That's a very good summary of how to run a basic research.
That's exactly it. And I can, now you look at all these, you just look around over the project, and I tell you that all these things that were there, that came, there was a happening like that did it. And that's when those things come about. Well, if I'd have stayed there, that's what I was going to work toward. To try, now we had a couple of situations where that had the prospects. One of them was in Siegel, who was doing work in organic and biology. And as, for example, one of the things he did was to spray pine trees in the very early spring with the plastic, so that when the sun got very bright, that it wouldn't evaporate the water and the pine trees wouldn't dry, killed. So he worked that up. And it got to be useful, but we never got it into a product. But that's what I'm talking about. And then you see, with something like that, you go down to the plastic people and they make it, and you go out and you really do something. Now he was one that had that interest and ability on his own. And he just did that. And at the last, well, when I knocked off up there, I had an Eton evening for me, and that's what I said. I said, now there's an example of what to do and how to do it. Siegel. And also Ribot. If it's Ribot and Siegel, those are the two guys. Now there's another fellow, Jim. What they tried to do, from the New York office, they were trying to set up a drug business. Try to get into the drug business. Now these people, this fellow and the organic people there, they were minded to do this, and we were trying to get over and get something started that would lead us into doing it. Now I don't know the details of what happened after a couple of years when I left, but what did happen is they tried to set up a company, and this fellow was put in charge of it. So that functioned, you see, that was what the place was about, and it had the makings of it. But, well, you know how it is. Anyhow, that's
Now then you came to Messiah College. How did you decide to come back to this area?
because that's where I came from.
And so,
I wanted something to do. At the same time, and I wrote this up in that little piece that I gave you. At Columbia, Dean Hawkes tried to get the science people to pay attention to the liberal arts projects, liberal arts people. And nobody ever, and I think that's almost a fair statement, went out of his way when he taught these courses for liberal arts people. You know, if they were required to take them. But nobody would go out of his way and think of what he ought to do to stimulate them to get them to thinking. Well, Dean Hawkes got after them. And this was, I would say it's somewhere around the middle 30s, 35. And he got after this, and he set up a 2-year program at Columbia. And they'd have one semester in physics, and one in chemistry, one in biology, and one in mathematics. And John Dunning gave the physics. And he did a tremendous job of showing them everything that went on in physics. What they learned, I don't know. But it was really a big demonstration of things in physics. Now, they had various people, one person, Thomas, do it for chemistry. I was I was doing something else. And then one year, one semester they had me do the chemistry. Now, I was started there as a lecture demonstrator. You put things in the table and then you just go from one thing to another. And you don't think too much about your lecturing. You don't get up there and give a well laid out, I didn't, nobody else did really, because you talk from your equipment, your stuff. So I would talk from this, and I did no thinking whatever about what I ought to do with regard to bringing these people around to understanding what science is all about in respect to the nature of this world. I was doing research. I was busy. I couldn't be bothered. And later, when I got down to Charleston, you know what I did down in Charleston in education?
I noticed it listed, but...
Well, one reason down there was because we took these people down, persuaded them to go down, and the first thing they said, well, how's education down there? We hear it's not good. So without thinking, I just impulsively thought I had to do something about it. So I went out and got acquainted with the people, and now during this period, I think it was the early 50s. People really got around to worrying about, like the Dean Hawkes, but other people were worrying about the fact that science and technology were just taking the country over along with business, and that the world was going to go to the dogs because there's nobody, they didn't understand what it was about and how to handle it. Which means then that you're back to trying somehow or other to make the liberal arts people understand what science and technology are about and its significance in regard to nature and themselves and the world, because they're the ones that are going to run the country. So, a president of Harvard, Conant, yeah, look at that, I remembered his name, Conant. 2 years of his time, he went away from Harvard. In 2 years, he took this as a major job to study this problem and had a commission working over it. And down at Charleston, I had figured we got these people down there and we ought to do something. So I got around to working with this, and I ended up now, they wanted me to be chairman of the state commission. Each state had one of these. And I said, I don't know these people in the state, somebody else has to go. But what I did was set up one of these things in Kanawha County. And I tried to get other people involved, other organizations, all the organizations I tried to get as representatives on this group, which I did pretty well. And I went around and come a time for election, I went around and talked to the various half dozen people who wanted to be on the board of trustees of the schools, and I ended up. I talked to the newspaper people ahead of time. I ended up talking to all these people and giving them my recommendation. And they took my recommendation. But I had to say something about the other two. So my recommendation was elected. And in the process, it more or less did got the educational establishment over to looking after education. So that's the way that worked. And then I got to, and the other things, in the course of all this, I was busy with the legislature. So they ended up putting me on a member of a committee of the legislature to look after, of the House of Legislation to look after education. And then they put me on another committee to revise the state constitution. Well, now in all of this, just to keep it on the right level, I essentially was Carbide. See, I didn't talk for Carbide, but Carbide was big stuff down there, so I was there as a kind of a listener from Carbide. So that's one of the main reasons why I could do things down there. Anyway, that's how that went on. And then when I was about to leave, I got around and here this thing was going on with, as I told you, with the president of Harvard. And so I thought when I was going to leave, why don't I get, and recalling this, shall I say, poor job I did with the liberal arts class in Columbia, I thought, well, why don't I just get around and see if I can do something. So I tried then to get to Dickinson and I did get started there with the idea of working with the liberal arts people, have them better understand science and technology so that they would be able to better develop ways of making our world work. So when I got there, I started at the bottom. I did lots of things, worked in the laboratory, but the one thing that was really of major interest to me, and I think very successful really, was I taught the history of science. Now the history of science was not something that I would go through all the 1, 2, 3s of how you learned how to do quantum mechanics, for example. No, it was how the humans interacted with in themselves and their environment. That was what I thought of. The history of your culture. That, to me, is the history of science, and I fortunately had books that worked on that. As, for example, the book related to what you would call chemistry was called the Architecture of Matter. And the book that related to biology and geology was called The Discovery of Time. See what I mean? But it was done well by two people that had done it extremely. Now, I had those books. And so, to me, that way of looking at science, I didn't talk about all those things, but I talked about the manner in which it worked. And that was a major advantage. And I would get people working on things that they were interested in. We talk about literature, and for example, how science affected literature, how that, for example, the laws of motion, Newton and the laws of motion, that set up a logical pattern for thinking. And so you have, then they decided that the world was set up by the originator of the world, and the world went clockwise after that on the laws, you see. That's the kind of thing. Then we looked at literature, how that Wordsworth was affected by this attitude. And then there was this book that had to do with the devil at the bottom of the sea. What's that? That poem, that long poem that was written back there around 1450. This is one of the major poems, big long book. That could not have been written 50 years later because of Newton. That's the kind of thing we talked about, and so on and so on. So, and then there at Columbia, that's what I did. And toward the end of that, I started working on how on the environment and so on. And then, come 70, they had enough of me up there. And I thought, now, what in the dickens am I going to do? Well, now let's see, down there was great. Why don't I go down and see if I can? Well, all right, so I end up then on the same mission down here for the liberal arts people. And that really was a mission. And I then was part of what they called the general education when I started. And I worked with that for a while, and then got over to helping I got over to working here in biology, gave a course in geology, it isn't geology, ecology. Gave a course in ecology. And in the course of this, course in ecology. I had students doing, trying to figure out how I got over into do chemical projects. We got doing a lot of chemical projects. That's what some of this stuff's all about. And, well, let me tell you what one of them was. See that tube up there?
Yes.
That tube, I was going to put ground in there. The length of that tube.
You mean
It had
soil?
ammonium nitrate in it.
Mm-hmm.
And in the course of time, that would generate, that ammonium nitrate is taken over to ammonium sulfate, I'm sorry, ammonium sulfate. And in the course of time, the ammonia is oxidized up to nitrate, in the process making N2O in the course. Now the N2O is a very stable substance, and it's generated out in the crops where they put this ammonium fertilizer, and the N2O goes up in the upper atmosphere, and up there, after 20 years, it'll diffuse up there, and up there it will interact with the ultraviolet and decompose into nitrogen ions or whatever, and anyway get around to decomposing ozone. Now it's ozone that enables you to be around, because otherwise you'd fry, because the ozone picks up that low wavelength, high energy. So the idea here was that I would then leave that stand, and then I would pull that gas around through my system here, freeze out the N2O, and then analyze it. And that was to be a student project.
Now, who did the glass blowing here?
Me.
You made all of those joints yourself?
Oh, sure.
And you learned that in graduate school?
I did that. That's what I did up at Columbia when I was doing those gas reactions with hydrogen and what was it? No, it was NO2 and CO.
Mm-hmm.
See, that's all a glass blowing. I spent a good bit of my time at Columbia glass blowing, so I did all that glass blowing. Of course, I can't do it now. And that was one of the projects. And another project, you have a lead gets into you and gets into your brain. I'm talking now about small children that eat paint, lead paint, and they become what do you call it? The mind there, because of the lead. So I thought, why don't I see what I can do, trying to find out where the lead goes in the brain. So I got some brains. They have rats here, so I fed rats some lead. Got their brains. And then we convert that over, you burn it down, and then you analyze for lead and for the other elements. And what I found was that the lead displaced copper and zinc from essential enzymes in the brain. In other words, the brain had lost copper and zinc, but there was lead in there. Well, that was the first experiment we did. Another experiment, was to look with, now there was an effort then made to show that all high pressure effects that you had were a consequence of cadmium that you picked up from somewhere or other. Now you know they used to put cadmium in all the hardware? Yes, all hardware was cadmium. And because of this, that got taken off because it increased the blood pressure. So I thought, well, let's see what we can do. So I fed some rats cadmium and measured their blood pressure. You measured on the tail. Measured their blood pressure, and after a while, I showed that they got an increased blood pressure. That was an experiment I did. Now the whole idea here was to see, now I'm getting over to environmental research. You see, by doing these, I get over. Now I want to give you another thing. I read in the book here that how some metals like cadmium and others are involved in plant growth. So I had an electrode here, and I thought, copper electrode. And I thought, gee, I'll just see what I can do. So now I want to get some roots. This is the spring. You couldn't get it. So what I did was to get some onions and put them in a little water. And after a while I got some roots. I put those roots in a beaker with my electrode and then put a little copper in, and it pulled the copper right out of the water. So I just went from one thing to another. And then instead of using roots, I'm talking to here, and I got over to using algae. That's how I got into algae.
That's how you got an algae.
Now you see, that's what I mean about this research stuff. Now when I get over into algae, I get back to the brain stuff again, and I think, now I can do my exchange, my exchange constant business. You know, I told you about that, and it's in that 94 paper. So I thought, now, why wouldn't I have the same reaction in the brain? Why haven't you acid functions in the brain that would work just like these acid functions in algae? So I got some pig brains, hog brains, we call them hog brains. Hog brains, I smash it up, centrifuge it, and get the tissues. Then I have this tissue now, and I then put that in a water suspension, and I put some cadmium on that, and the cadmium's picked up. And furthermore, not only does it pick it up, but it displaces protons. Now, where are those papers I gave you? That's the brains paper, isn't it?
Let's see. Yes.
That's it. That's the paper. That's how that research got started. Now, you know what I'm going to do this fall?
No,
This summer? Well, I got in just casually was looking over some literature of a fellow who'd worked with crabs, showing how crabs could stand going from salt water to fresh water. That is, the tide would come through. Showing how that they, and I got the idea, here you've got fish with gills. He worked with gills. Here you've got fish with gills. And why wouldn't this these toxic metals that you're dumping into the waters, why wouldn't they, when they go over the fish gills, be picked up by the fish gills by this same reaction? That's what I'm going to do this summer.
Now you're going to do this all by yourself.
Oh, sure. Now let me tell you, I want to work by myself. You know why? Now I'll tell you why I want to work by myself. You know those years that I was hoofing around on the Manhattan Project and down in Charleston, then up in Tarrytown, and look at that guy, Tom Wilson. Jiminy Christmas, why can't I get it? And then up at Tarrytown, I would sit there in my office. Gosh, out there is Rabot. Look what fun he's having. I'm not kidding you. And so it went. And then, you see, up at Columbia, I was just one of the very few professors up there that did a lot of their own work. They all got graduate students to do their work for, but I couldn't, I just had to work myself. So I do all my glass blowing, do everything. I just had to work. I had to work with my graduate students. I just had to work with them. And so going through these years of sitting up here in administration and doing nothing, my head got sorer and sorer. And when I had a chance of doing, now, that's what I want to do. I just can't stop. You know, I just have to. My back hurts, and I can't walk, I can't see, and I can't hear, but I can't stop. That's why. I'm not kidding you.
No.
You just hold yourself for a while. You'll get there too. But that's the reason. And here, as I think about it, I think it's mainly my farm. You grew up on a farm. You've got to have your hands on something all day, every day, night and day, all the time. Now let me tell you what I did one summer. We had that small farm up there, and so one summer, I guess I was 16 or 17, maybe 17. I ended up, now I don't remember quite how this happened, but I ended up working in the stone quarry down here at Bowmansdale. Now Bowmansdale is about a half a mile down here. And this is limestone area, and that's it was in a beautiful limestone, and they quarried limestone and made limestone powder and around over the farms. And so what did I do down there? I'd hammer on a drill to make a hole and blow it up, and then I'd break up the stone with a sledgehammer. What was it, 10-pound sledgehammer, hammered all day, breaking stone. All right, now what did I do? I get up in the morning, I'd feed the hogs, and then get down here about 7:30 from out there in the farm. And I would have carried my lunch along, and then I'd work till about 6 o'clock and then walk home. And then do some more work at home. That's what I mean.
I came to the same conclusion about growing up on a farm as
I can't help myself. That's what I
if you
mean.
aren't doing something with your hands, you don't feel like you're working.
I don't want this to be something that I get out there and deliver. It's something I can't help. I just have to. I just have to do something. Can't help myself.
Now, how did you come across the article on the crabs?
Oh, you turn that off and I'll tell you. They, you are asked to recommend reviewers.
Mm-hmm.
And as, well, anyhow, that's what.
But you're still getting papers to review at 94.
I get about one a month.
Oh,
That's about the way it's working out. And now this, I got a paper from, did a review, well, that's where it's either, the other thing that has given me some, I'm satisfied that I'm on the right track, is that we've been invited to these various places.
mm-hmm.
And so far, we've had invitations to two symposia in the American Chemical Society, the international meeting that I told you about on the relation of metals to microorganisms in MITS, that was international.
Mm-hmm.
And then this fall will be the third meeting to the Engineering Foundation. Now, the Engineering Foundation is, they're involved in trying to do something about mining operations, and also, well, primarily mining operations. And this stuff is used, algae is used in the mining business. They, out in the lake, they will grow algae and flood their waters out there or something like that. That's the kind of thing that goes on. And as a matter of fact, the last paper I reviewed, which was just about 2 weeks I sent it in, was by some people up in Massachusetts. And what they were doing, well, they were working with this green algae that grows in open waters in the summer,
Mm-hmm.
chlorella. As a matter of fact, see that long, those two pipes back there, those big ones? They're pipes. There's two back there. Two like this.
Oh, yes.
I grew chlorella in there.
Mm-hmm.
And what I did was put I got it and you put a little in and I bubbled CO2 through it. And after about 4 days it began to look just slightly green, and then in 5 days it was deeply, and in 6 days it was deeply colored. And then I used that to do research with that chlorella. And now I'm going to get back to that again, because one of the problems when you're dealing with a solid in which you have a metal in solution, and it's got to get into and around through that solid. The problem is, how do those ions get in there? And how do they diffuse around into the solid? Well, now with this other stuff, thing is called a tissue grinder.
Sure.
So what I do is to put the stuff in there and run this with a motor. I have a motor right over there. See, it's sticking in the hood.
Yes.
I have one there, and I buzz this, and that breaks it up. See, that'll break it up. See, I buzz that, and then I take, and then I use it. Now, I want to put this back where it was.
Yes.
Because I don't want to. See, I can't get things mixed up.
You're still organized.
So, what you do, what I do, is to break it up that way. And now you still have the problem of what is the holdup of the manner in which these ions get from the water solution into and through the solid transport. That's what I'm looking at. And that's another of the major problems. And that now let me tell you about the chlorella. Chlorella is ordinarily when algae grows, a lot of it grows in just a fiber, one cell on top of another. Now with chlorella is just a single cell. It's just single cells. So what I'm figuring on doing is to grow some this summer. I'm going to try and get some chlorella. If I can't, then I may grow it. But what you have on the chlorella then is not a package of cells, but a single cell. And so with my method of now here, what I've done is to put a sample of algae. This was Valkyria algae in a little beaker, and then I put some. What was this? Is this time?
Time. Seconds.
Yeah, but I think this is.
It's a log of copper.
Yeah, but I think this was copper. Yeah, copper.
Yes.
Logarithm of copper. So I analyzed, I handle this awful fast because I try to do this, say, within 20 seconds. I get a sample and then 30 and 40 and 50 for my time factor here. And then when I plot the logarithm of the concentration outside, I get these slopes, different slopes. Now, I'm trying to figure out that this last one is diffusion into the solid phase, and that this has to do with something that's on the surface, you see. In other words, I'm trying to interpret this in respect to the manner in which this stuff transports from the solution into the solid. That's what I'm trying to do. And so now you see when I get that single cell, I don't have the other
Stuff
complex around it. And I might say that let's see, that was the, no, that was that page. Now here it is again.
Oh,
Now this is
You do.
peat moss.
mhm.
That's a peat moss.
And so it fits the
So
low
I'm
at later
getting around
time.
and getting this as a general phenomenon.
Mhm.
But now, what the dickens causes that? What makes that? Is it particle size? Is it diffusion inside the
Mhm.
particle? And I'm arguing that the last one
It
is
diffusion.
a diffusion inside the particle. While this is a fast one affecting the surface. Well, that is, there it is.
It certainly is there.
So, now, when are we going, when are you through with this?
Well, if you want to take a break, or if you're
Oh,
done.
I don't
with-
need breaks.
No?
Let's finish what you want to do.
Okay. Well, I would like to get some pictures of you doing something here in the lab, just pretending you're doing it if I could.